In this video, we are going to look at the maths behind neural network, particularly what happened during forward propagation and backward propagation. So, just a little bit summary of what a feed-forward network is. A feed-forward network is one network which contains only like unidirectional flow. By unidirectional flow, I mean is that it contains forward propagation layer, and that too in a simplified neural network kind of a way, like this straightforward connection between these layers and these layers. So like as you can see, these connections are getting formed across the layers, right? So this is feed-forward network. Unlike like CNN or LSTM, those are more complex networks because they have a different architecture than this. So we are going to explain how feed-forward network works. Now, let's take example. What we are going to do is we are going to build a network which contains two layers, layer 1 and layer 2. Let me pull the pen. 1 and 2, 1 and 2. Okay, so how our network will look like is, let me show you by a zooming out view, that it contains initially two nodes, I1 and I2, and it contains three hidden nodes in a middle layer, this, and then it contains the output nodes. So the network is 2 by 3 by 2. Okay, and like it's a fully connected network. By that I mean is like this layer and the previous layer have all the nodes connected, means every node in previous layer has a edge towards every other node in this layer, and similarly the other one. So we have done naming convention such as you can see here. So I means input. Okay, W denotes the weight. W1 means the weight of first layer, and the subscript means that W111, it means there's a weight from one of this layer to one of this layer. And similarly, if I say W112, it means there's an edge from here to the second node of this layer. And similarly, like for the second layer, it's a W2, which is identifying with which is present. Now, when all the weights are collated, they are going to collate it into N1, which means it's a summary of all the information which is coming from previous node. And then we are going to apply an activation function, and the result of the activation function is stored into A1. E is our error term. We have E1, which is the error at the final node 1, and the E2 is the error at the final node 2. B is biases, means extra bias that we are adding, and this is the naming convention that we are going to follow. So let's start with forward pass. By forward pass I mean is when the information is flowing from this direction to this direction. Okay, now as I have told you above that we have two layers. First is this layer, or rather than the output layer, let me put a marker here, and the second is this layer. So the first calculation is going to perform here, and the second calculation is going to get performed here. So now this is our equation. N1 means this node, and similarly N12 means the second node. So this information, as you can see here, it just multiplying the, okay, let me pull a, where is that, it's just multiplying the input of the first layer and the weight which is coming to here. For example, let me just show you this information. Let me just erase everything so it should be more clearer. Okay, so like, so this information or this one contains I1 multiplied by this one plus I2 multiplied by W1 21 plus this weight, and this is the exact same equation. So, and similarly, like for N11 we have N12 and N13, which are these nodes, and after that we are going to obtain A1 by applying some activation function on the data we have obtained here. For example, this we can obtain after applying some transformation, and this is usually your activation function. Once we have here, the story just repeats. It means we are going to calculate these values using these inputs, again similar what we have done earlier. Okay, and the equations are similar, like all the edges which are being incident on this node are being combined. So now when I say N21, which is this one, so A11 multiplied by this one, A12 multiplied by this one, A13 multiplied by this one, and plus B21. Similarly what you're doing here, and then similar activation function. Now one thing I notice about this is not like, this is easier to explain, but how we are going to implement it, by that I mean is how we are going to mathematically implement it. So all the equations that we have seen here can be summarized in matrix form, which are easy to compute when we are dealing with computers. So I is a 1/2 matrix. Why? Because we have 2 neurons here, right? And similarly your W1 is 2/3 because it is having 2 neurons as input and 3 neurons as output. So that means your W2 should be 3/2 because 3 neurons as input, 2 neurons as output, right? And this A11, so what should be its dimension? It should be pretty straightforward, since we have 3 neurons or 3 activation at layer 1, its dimension is 1/3, and 2 activations at layer 2, its dimension is 1/2. As you can see here, we have 3 activation at layer 1 and 2 activation at layer 2. Let me just erase it again. So that's the matrix dimension that we are going to use. Now like, what's the equation for calculating values like n? So it's straightforward. It's I times W plus B. Okay, I is 1/2, W is 2/3, and your B is 1/3 because it is connecting to 3 nodes. Okay, as you know, when we multiply a matrix, the result is always first column, first means value of the first dimension of the first matrix and the second dimension of second matrix. So it means the output should be 1 by 3. And 1 by 3 plus 1 by 3 is again 1 by 3. So as you can see, here's what you're using here. So you have one matrix like n111, which is 1 by 2 plus 2 by 3 plus 1 by 2, which should be around output dimension should be around 1 by 3. So this is our output dimension. There's a typo here, that should be B13 here. It's missing here, so that's how it should be. Okay, so now coming on to next equation. Now once we have computed like the first layer forward pass matrix, let's compute the activation. So similarly, as I've shown here, in normal equation case we have used F, but right now we are using actual activation, which is tan H. You can use any other like ReLU or leaky ReLU or any other activation function. Okay, so this is your output equation for first hidden layer. Now similarly, you can have the output equation for the second hidden layer. So whatever we calculated in the first hidden layer, the output of this layer will act as the input for the other layer. Now the output is a 1 by 3 matrix. So it is a 1 by 3 matrix. This is 3 by 2 matrix. As I said earlier, 3 matrix, 2 matrix. So it's a 3 by 2. And this is 1 by 2. So here you're having that. Where's that? Let me see. Yes, here you're having that 1 by 3, 3 by 2 and 1 by 2. So 1 by 2 plus 1 by 2 is 1 by 2. So now coming back onto the expanding equation, you can just use this equation and just pass the activation function to this. So the output of this will be fed to the next activation function, and you get the result like your final activation. So there's a typo here actually. This should be around A22, A221, A22. Okay, and so this is how your final A21 and A22 will look like. A21 and A22 will look like. So now this is our propagation. Now the forward pass equation are straightforward. They are just matrix multiplication, right? So you can pretty much arrive at it. So they are straightforward. The tricky part is when we are calculating derivative. So that's where we need to give focus. Now this is our network, as we have already stated. Now what we are going to do is we are going to calculate derivative, which is how much your error is going to get impacted with respect to each weight, right? So in the second layer we have around 6 weight. So we are going to calculate like the error with respect to W211 first, and the similar process can be applied to other weights, right? So now the error, which is ET, can be comprised in like as a combination of E1 and E2. Okay, so and in simple terms, just the output minus target square, and kind of a neural network. But let's just keep it like E1 and E2, whereas E1 is the actual value of this, the label value of this, and the obtained value from the forward pass. That's your error. So once the error has arrived, each weight is contributing something towards this error. Our aim is to find like what these weights are contributing, and once we find out, we are going to readjust their value based on backward pass or backward propagation formula. We are going to discuss that too. So now we just pick this one and the others will follow. So what's the error term with respect to W211 look like? This is our partial derivative. So we are going to use calculus here. So now those who are familiar with calculus know about the chain rule. It means if we can form an expression which can be simplified into this expression, we can pretty much substitute like this. For example, ETW211 can be written like this, like this, like this, because simplification, this cancel this cancel this, and in turn we only obtain like ET divided by W211 partial derivative, or delta you can say, right? So this is our grand equation. By grand equation I mean this is our main equation, and we are going to solve all the sub equation. So when I say equation 1, it means equation 1 is this, equation 2 is this, equation 3 is this. So let's solve for equation 1. Error respect to A21. So this is your error, final error, which is the actual value, like the target value at 1, and the obtained value. It means the target value and the obtained value. Obtained value means during forward propagation pass. This is our A2 minus 1, A21. Similarly, the other as well, right? Because we have two error terms, E1 and E2, here, here. So you can just expand like A minus B whole square formula, and you obtain like this. So now just take a partial derivative, like by that I mean is assign this. If you put it here, you also have to put it here as well. So when you take a partial derivative, so when you take a partial derivative A21, this will cancel out, because let me just clean this up, because you are taking derivative with this term does not contain any A21, cancel out. This contains A21, this will come here, so this is $A21. This contains A21, which is this. Now this whole equation does not contain any A21, so this all will cancel out. So in a nutshell, you obtained half of 2A21 minus 2T21. In simplification, you can just cancel out this, you will obtain minus T21 minus A21. So this is your first equation output. So we have obtained our first value. Let's take it out. Now about the second value, A21, N21. So A21, what is A21? It's just the activation of N21. Now software equation can also be written as like 1 upon 1 minus e to power minus N21, whatever the value is here. And if we take a partial derivative with respect to N21, this is what we get. Your second equation also fulfilled. This also check out. Now the last one. What about the last one? Similarly, like earlier, we just use the equation for N21 and just take a partial derivative with respect to W211. this contain W211, so this will be here. This does not contain W211, cancel out. This is your third equation. Now put everything into your grand equation, which is this, the same one, right? So after putting all the three values, you get this. You can simplify it by just playing around, right? So when you simplify the equation, what you get is, you just rename these value as partial derivative delta to 1, because this is respected to 1. It's just a simplified version of this. So this is your error term with respect to W211. Similarly calculate for each and every weight, right? So when you obtain your error term in a mathematical equation, so as you know that during backward pass, whatever the contribution of error is, your weight like W211 is going to readjusted. So this is your original value of W211. Apply a learning rate times the contribution of W211 towards total error, and you obtain your new value of W211. So now let's calculate the backward propagation during first layer. So earlier we calculated backward propagation in the second layer, which was a little bit easier, because as you can see here, when you were trying to calculate for this variable, only this error term was being calculated. So it means E2 has no effect on W211 when calculating backward pass, because the W211 is only contributing towards error 1, right? But that's not true for this. Like if you want to calculate what's our error with respect to W111, we can see that during forward pass this has been split into this and this, so it's contributing to both the errors. So it means both are going to play a part when adjusting its value during the backward pass, because it is contributing, right? As you can see from these arrows, like all the errors are back propagated. So we are going to calculate this, and similarly the rest of the equation can be solved. Now like as you have already figured out, we are going to use a grand equation here. By that I mean is, we want to calculate total error with respect to W111, our objective. Let's use chain rule to expand this same term, right? And let's further extend this part. By that I mean is, ET is combination of E1 and E2, so it can be written like this as well. Now we have three equations to solve. Similarly, during the second layer backpropagation check, the first layer backpropagation also has three components. One is this, other is this, other is this. So let's solve equation 1 first. Equation 1 can be further written like this, right? Again chain rule, E1 A11, E1 A11, E2 this. Now we have already calculated this, and its value is this, minus E21. Why is that? As you can see, same equation, ET is even, because as we know W211 is only contributing to E1, there is no E2 involved. So this is the same equation as we have here. So we already know its value, which is this. Now we need to calculate N21 with respect to A11. N21 is equation is here. It's the same equation we have obtained during forward propagation. Like all the metric equations are here. So we just plug and play the value, right? So now when we take a derivative with respect to A11, all the element which does not contains A11 will get cross out. Only this contains A11, so W211 remain, and this we have, as I mentioned, it has already been calculated. So our first equation value will be this. Now this is E1 A11. Similarly, E2 A11 can also be calculated with the same value. Just replace 1 by 2. In a general, it can also be written like this. First equation solved. In grand equation, this has been solved. Now what about A11, N11, and what about this? So this is our second equation, this is our third equation. Now I'm not going to solve this, but a derivation is available on the internet, so you can just, this can be simplified into this, and the third equation is simple, like you just take a derivative, N11 W11, all the element which does not contain N11 will cancel out and only I1 will remain. Now you have all the three equations. This is second, this is third, and this is first. Just substitute here. After substituting, you obtain this value, and this value just simplify, just write it like this. Just we are renaming. So this is your error term with respect to W111. Similarly, calculate with each and every one. And as I mentioned earlier, that you can use this formula, which is this one, there as well. In there, you are just going to use that W111 equal to W111 minus learning rate with respect to ET W111. So this is your complete maths behind for feed forward network. As you can see, we calculated the equation for forward pass, and then we propagated the error, which is E1 and E2, and we calculated what would be the contribution of each weight to the total error. Once we know the contribution, we can just readjust its value based on contribution towards total error, which is using a learning rate and the error term as mentioned here. As mentioned, let me see where. Here